So let's see, where did we leave off? We had looked at the torque here. We found that the torque is in this direction. And then we calculate, that means the stress induced at point B here is a shear stress on B due to that twisting moment My of 7,200 pounds inch, which we calculate by the torsion formula, which is this internal torque times the radius or the distance from 0 to point B divided by the polar moment of inertia, which is pi over 2 r to the fourth. Okay, and here is that stress at point B. And again, we want to think about what direction that shear stress is in. And then we looked at the shear force in the z-axis. And because this is at the very top of the section, my shear stress here is 0 due to Vz. So here, shear stress equals 0 due to Vz. And then same thing here, I have a moment acting about z, but I have no distance from the neutral axis of the mz, the moment about z. So therefore, the normal stress equals 0 due to mz. Yeah? All right. So we've done a major part of this problem. We are like 75% of the way there. We've done equilibrium, and we have to draw the representative volume element. So here, this is an insane problem. There's like 8 steps, 9 steps. Gosh. Here, 8 is draw the RVE at point B. Okay, and so now we have here, essentially we have components that are important for us. And what I want to do, so we have Vx, Mx, Ny, and My that are causing some sort of stress at point B. So let me start here. I will draw here a kind of a 3D of the cross section again, right here. Point B is up here. Here is my, we said X, Y going down this way, and Z going up here, right there. And here's the rest of my solid that is, it's cut off obviously. And here we are again as the observer, right here. Now what I want to do is zoom in on this point right here, okay? I want to zoom in on where this is point B. And this time I'm going to draw point B as a square right here. The face of point B right here, okay? And here, I'm going to draw this a little bit bigger, is the face of point B in red. And the rest of my volume element is this cube that would be going into that. This is not the best cube in the world, but hey, that's why it's there. Or at least I'm drawing it, right? So there's that face here, okay? So now let's start. Let's look at the normal stresses, okay? Let's start with let's start with Vx. Vx is a shear force going to the right here, and causes a shear stress of 212 psi. Yeah? So here, this is where that face of B is. Here's my B, right here. That means on B, right here, for Vx, did we call this Vx? For Vx, right here, I have a shear stress here of, what did we say that was? 212 psi? What was that number? Someone's got to read it to me. I can't keep going up and down. It was 212. So this is 212.2 psi. Okay. Plus, I'm going to redraw the cube again. Right there. I'm going to redraw that cube. Now let's look at mx. All right. So for mx, did it cause compression or tension at that point? Our moment about x. What was the value, mx? Compression of 6.11 ksi, which means that I have here 6.11 KSI. Yes. Plus, now let's do the next square, next cube. Okay. In a perfect world, all of these would look exactly the same, but I am not perfect. I am just a man, unfortunately. Or I could be a machine. Or maybe, who knows, a professional bowler. Huh. I would enjoy being a professional bowler. All right, so here, okay. Let's see here, NY. Right, so here now we have NY. Let's look at NY. That's the other one, NY. So here, let's look at this one as NY right here. And the normal force on this surface, was it causing tension or compression? Tension. And what was the magnitude of that tension? What? 0.255 KSI. Awesome. Right there. Then, and last but not least, the moment about Y. Like this, right here. The moment about Y right here. And that moment about Y, just because it was close, is going which way? We have the torsion here, meaning that the torque is going like this. That's the direction of my right here, like that. Yeah? Therefore, the stress on B right here is like that, with a magnitude of, what did we say? 4,584. 4,584 PSI. Woo! Okay? Oh, man, right? Okay, so here, this is a normal stress, a shear stress, and a shear stress. Just like we learned the very first week. There's only two types of stresses, normal and shear. And you can only add up or, add normals together and shears together. So now when I put all of this stuff together, put all this bad boy together, bam, right here. Boom, boom. Here we go. Right here. Right there. Okay? Like that, right there. And then, so now I got to say, 212.2, my shear stress here, this tau, is equal to 212.2 PSI plus 4,584 PSI, which is 4,700, 80, what is it? 4796? 4796.2 PSI right there. That is my tau. Bam. Okay? Now I can draw the rest in. That's my tau here. And my normal stress, sigma, which I'll do in, how about blue? Sigma is, 6.11 KSI minus 0.255 KSI, which is 5.855 KSI. And that is causing compression because this is my dominant arrow here. So this right here is 5.855 KSI, sigma, and I have the equal and opposite right here. And this is my state of stress at point B. Right there, right? And if I were looking at it from 2D, finally now, if we could look at it from 2D, let's say I'm looking top down like this. I'm looking down at it right there. Then I would see here on point B, same place where that letter is right here, I would see on all sides right here, this would be tau equal to 4 0.796 KSI with compression here of sigma equal to 5.855 KSI. Wow. Yeah, that's it right here. And now I could say find the principal stresses, find the maximum in-plane shear stresses at point B. Using what? Yeah, Mohr circle stress transformation. Right? And that would be, gosh, that's like 75% of mechanics of materials right there, all in one problem. If I did that. Yeah. Right. Don't, so yeah, right. Moral of the story, don't mess up on the internal loading and reactions. Oh man. Okay. So hopefully that was insightful. You know, if you have the time, try point A. Although point A is not going to be that bad now because we already have the internal loading, right? So if you feel so ambitious, try point A, okay, on the same problem. All right.